welcome, mindsetters. How are you? I am terrible, guys. Guys, a little bit tells me that you grade 11s have been waiting anxiously for your mathematics. And guys, helping us today is our awesome teacher, Dina. How are you, ma'am?
Hello, Tepu, and hello, everybody else.
What
How
are we
you
doing
doing
today?
We are doing some trigonometry, some trig graphs. The grade 10s have just left off some trig graphs, and we're just continuing with the graphs as well.
Grade 10s. If you're watching, you can still join us. You're welcome just to, step up your game a little bit and surprise your teacher. But for now, Dina, you can take the board.
Thanks, Tepu.
Guys, while you're on that one, remember to visit our website. It's learnextra.co.za/live, or simply go to our Facebook page and like it. It's facebook.com/learnextra, or follow us on Twitter. Simple as that. It's @learnextra. Yeah. And guys, we thank Macmillan for sponsoring the show. All the notes that we'll be using today are from the Macmillan textbook. You can go and get it, the grade 11 version. Or simply, guys, don't forget to go to our site and go to our site, and simply download the notes for today's show and do with them at home and paste them on their walls, on your whatever, and just have fun, guys. Trigonometry with Dina. Dina, you can take the board. Okay, but before she does that, guys, please, on our Facebook page, ask as many questions as you can. Challenge me as hard as you can, and I'll ask her as many questions as I can. But for now, Dina, take it over.
Thanks, Tepu, and welcome grade 11s and maybe some grade 12s. We're doing some revision, and some grade 10s if you just want to extend your knowledge. So let's have a look at some of the trig functions. You did in grade 10 look at the transformations, changing the amplitude and changing the vertical shift. But today we're going to look at some period changes, and we're going to have a look at some horizontal changes. So those are the two new changes coming in. So we will revise very briefly what the amplitude change does, and we will look at some key concepts as well. But let's go straight ahead and see what the objectives of our lesson are for today. Okay, in this lesson, we're going to revise the terms that we use, often used in trig functions and in some other functions as well. We're going to look at domain, range, amplitude, period, maxima, and minima values. We're going to investigate the parameters A, B, P, and Q on the parent trig graphs, so that we'll eventually look at what does A sine bx plus Q, as well as y equals sine of x minus P looks like. And then we're going to do that for the other trig functions, the cos function and tan function as well. And then I'm going to draw very selected trig functions which undergo the transformations of amplitude, period, vertical and horizontal shifts, focusing on these 4 transformations because that's what we'll be asked to sketch for examination purposes. What are the key concepts? And you've heard these words before, so just to revise them, domain is the set of all the x values which a function can have. And in terms of trigonometry, we're looking at how many degrees a function can take on. The range is a set of all y values which a function can have. So domain is the x, and if you remember that domain starts with a D, and that stands for our x values. Range starts with an R, and that's for our y values. So x, y, domain range, so that you don't get those two words mixed up. The amplitude of a graph is always defined as the difference between the maximum and minimum y values. And the period of the graph, very specific definition for period. It's the number of degrees that the curve takes to complete one wavelength. So we'll look quite intensely at the period of functions. Having said that with our key concepts, I want to now look at the graph of y equals a sine x, which we are calling as a change in amplitude. And the graphs have been sketched for us, and just below the graphs, we've got a table that just shows us those key features: the domain, the range, the amplitude, and the period. And if I had to draw the parent graph, the sine parent graph, then it would look something like this. We would have a maximum at 90, we would have a minimum at negative 270, and a 0. So continuing the cycle this way, we would have these values, so that our sine graph, or what we call our parent graph, would have a range that goes between -1 as the minimum to 1. So all my sine values are found between 1 and -1. And we're now looking at the graph y equals 2 sine x, which is this graph over here. And we're looking at the graph of y equals -1 sine x, which is this graph over there. So just to talk about it, you'll see that the yellow graph has got a maximum at 2, and the purple graph has got a minimum at -1. So looking at the range, it's still -1 to 1. The range is still the same. The range for the yellow graph has changed because the coefficient is now 2. So changing the coefficient of the trig function will change its maximum and minimum values. And the way that we can actually plot those is very easy, because our parent graph has got y values that start at 0. So this is just my y values. They would be 0, I go to 1, I go back to 0, I go to -1, and I go back to 0. So my quadrant angles, 90, 180, 270, 360, have got these critical maximum, minimum, and 0 values. And if I want to then see what is the effect of that coefficient of the ratio, I would multiply each of those y values by the new function or the new coefficient a, and I would now be able to get what those new critical values would be. So the amplitude, very easy to work with. Take your parent graph, multiply it by the new coefficient, and we've got the yellow graph if it's 2, and we've got the purple graph if it's 1, if it's -1. -1, notice, it's just the reflection of the blue graph about the x-axis. So we've inverted every single blue value by a value of -1 across the x-axis. So that would be our amplitude change. Then, if we look at the graph of y equals a cos x, still a change in amplitude. Notice that for the cos graph, my y values starting at 0 would be 1, 0, -1, 0, 1. And this is not meant to be a little negative here. That's a 0. So we have, there's a 0. So if we now have this a value that we're multiplying the cos by, you would take your critical values or your quadrant values and you would multiply it by a. So in this case, we've multiplied it by -2, and in this case, we've multiplied it by half. So we've taken half of those values. What are you expecting to happen? You're expecting that range to also halve, and that's what's happened. Whereas over here, you've multiplied it by -2, so you've increased that maximum and you've decreased that minimum as well. So the graph's indicating how the amplitude has been affected by the change in that coefficient. Now notice that the parent graph of cos, let's do it in blue, would start at 1, it then goes to 0, it then goes down to a minimum, back to 0, and over there. So your parent graph of cos does that, and it takes 90, 180, 270, it takes 360 degrees for us to start repeating the cycle, because we're going to decrease over here. So one wavelength is what we call the period. It takes 360 to complete the cycle. And then my domain, in this case, it's because I've restricted my values to -360 to 360, but the range is dependent on what you've chosen for your domain. And so in this case, the amplitude of this graph, remember, it's the difference between the maximum and the minimum value. So it would be 2 plus 2 is 4, divided by 2 is 2. So the amplitude is 2. The amplitude is not the coefficient. It's referred to as a distance. So just to illustrate that you can have negative coefficients, but amplitude refers to the distance between the minimum and the maximum and then halved, so that would be 2. And the period in this case would be 360. Right, now the one that I'm really interested today is the change in the period, which I think a lot of grade 11s haven't seen yet. We're going to now tackle how do we see the period change, or what affects the period of a graph. Okay, and so the parent graph y equals sine x has been drawn. Let's stick to parent graphs in blue. So that would be this graph over here. My y equals sine x function. And what we've done is we've now plotted y equals sine 2x. And by plotting that graph, we notice something new happening. Okay, I think you see it straight away as I'm sketching, is that you don't only get one curve between 0 and 360, you now get, I go up, I decrease, I repeat again. I'm actually getting 2 cycles into, or 2 wavelengths into the period that originally was my blue function. So sketching y equals sine 2x has done something to the period. It's halved the period. So the period has now become 180 degrees, or a half of the period of the parent graph, which is 360 divided by 2. So certainly we think that there is a relationship between the coefficient of x and its period, and we can see that if the coefficient of x is 2, the period has actually been halved. So we could say that there's an inverse relationship between the angle, or between the coefficient of the angle and its period. So let's look at this in more detail. Okay, so if we had to look at the coefficient of the angle, that very number will impact on how many cycles we're actually going to get. So we saw just now that if it was y equals sine 2x, then there are going to be 2 cycles of that parent graph in a period of 360 degrees, or in a distance of 360 degrees. So here we have sketched y equals sine a half x, and we are saying that there is now going to be a half a cycle between 0 and 360 degrees, and that's exactly what's happened. There's your maximum at 180, and it goes to, now remember, the sine graph, the parent graph, goes through here, and it comes down there. So we've only got a half a cycle, whereas sine 2x, okay, it's now doing 1 cycle and 2 cycles in the 360 degrees. And I'm comparing these graphs to the parent graph y equals sine x. Everything I'm talking about relates back to y equals sine x. So that period, this graph's period, is 360 degrees. We're saying that this graph's period is 360 divided by a half, which is 720 degrees. And we're saying that this graph's period is 360 divided by 2. So we take 360 degrees and we divide it by the coefficient of the angle to calculate what the graph's new period is. And we can see it very well drawn here. So understand, domain and period are 2 different things. Domain is how many degrees you want to sketch the graph over, whereas the period is how many degrees does it take to complete 1 cycle. We can definitely see here that the sine cycle, only a half of it has been sketched. There's another half of it missing. Hence the period is going to be 720. Even though I've stopped sketching at 360, that does not mean that my period is 360 degrees, because I can carry on sketching beyond 360 degrees, and therefore my period would have to be 720. So how many degrees would I take to complete that curve? Now, what we would be interested in is, yes, I've sketched the graphs for you, and it's lovely to have them up, but if I was sketching this graph for any given domain, and I wanted to know where I begin, you would always begin with a period. So you would take the period of the parent graph, which is 360 degrees. You would then divide it by 2, and you would now say, I'm going to complete one sine cycle. And remember, the sine cycle is having 0 maximum, 0 minimum, 0. So that's what we're expecting of a sine cycle. And I would then say, I need to plot 1, 2, 3, 4 values across 180 degrees. So I need to divide that by 4 in order to get to what my quadrant angles are going to be. So that would be my first value, my second one, my third one, my fourth one. Every 45 degrees, I'm going to be plotting that sequence of values.
Okay, thank you, Dina. Guys, please, guys, ask those questions on Facebook, guys, and please work with us. It's information overload, yet so easy here on Mindset, guys. But for now, for a quick ad break, let's go drink a bit of water and refresh our minds. Let's go for an ad break. Okay, Mindsetter, welcome back. I hope you had an awesome ad break. But for now, guys, please, on our Facebook page, don't forget, guys, to ask any question that you have. But for now, I like everything that's been happening, the energy on our Facebook page, and I know that you are anxiously waiting for the notes. Guys, the notes are not ready yet on our page, but you can look for them as soon as tomorrow or today at during the midnight. From that time, they will be on our website. But for now, let's continue with Dina. Dina?
Thanks, Tepu. Yes, I would like to continue from where we left off before the break, which is looking at the period change with trig functions. And we looked at how sine had been sketched, and when we multiply the coefficient by a new number, we will find that the period has been affected. And I would like to now look at the cos function and take one of those, a selected cos function, in order to show how that period has actually been affected. Okay, we're going to first of all take the parent graph features of cos x to sketch the graph of y equals cos 3x. And I want to emphasize, please do not point plot values. Do not take your calculator, substitute an angle, times by 3, take the cos of that, because that is a really big waste of time. You need to be able to understand the transformation from the parent graph. So the first thing we're going to look at is what is the sequence of y values in the period of the parent graph. So we have maybe we could say parent graph has got y values that begin at 1, they then decrease to 0, to a minimum, back to 0, and again back to 1. So this is the sequence of y values that we have every 90 degrees. So every 90 degrees we're either getting a maximum or a 0. So there's an interval of 90 degrees that separates every 0 from a maximum, every maximum from a 0, every 0 from a minimum, etc. Now what happens when your period changes is that interval is either going to get smaller or that interval is going to get larger, depending on that coefficient. If the coefficient is bigger than 1, then you're going to find that the values decrease. If it is less, it's between 0 and 1, you're going to find that the values increase. So there will be a change of those intervals. So at the outset, if we know that this is fixed every 90 degrees, we now know that if we're going to multiply x by a coefficient and it's going to affect those intervals, we want to know what the new intervals are. Because remember, the y values are fixed, but the intervals, the angle at which you're plotting, will change. So let's look at what is the new period if we have cos 3x. The new period is that the features of the parent graph is that its period is 360 degrees. So we now have that the new period for this graph will be what the parent graph was, and we're going to divide that by 3. So the new period is 120 degrees. Now, if we start at 0 degrees at 1, we now need to fit 120 degrees across 4 values. That's really what's happening. Remember, the parent graph has intervals of 90 degrees. We now need to get those 90 degrees, and we need to get it into a shorter interval in order to cope with having a new period of 120 degrees. Question is, how many degrees will it take for us to plot these intervals? So this is really the second thing that we want to do. We want to take what are my intervals between the x-intercepts and the turning points. And how do we find that out? We take our 120, we take our new period, and we said there are 1, 2, 3, 4 that we have to plot. So if we divide it by 4, it's actually equal to 30 degrees. So our new interval is now 30 degrees. So at 30 degrees, we're going to plot 0, at 60 degrees, at 90 degrees, and at 120. So this is going to be 30. Let's just undo that. So that's 30 degrees, 60, 90, and 120. Okay, so once you know that, once you know the new period, once you know the new intervals between the maxima and the zeros, you can now sketch that function to infinity or negative infinity without a problem. Your job is always to determine what one cycle will look like, because once you know what one cycle looks like, you just keep on repeating. So you'll find many questions usually ask about a sketch that has a domain from negative 180 to 180 degrees, or from negative 270 to 360 degrees, so they've got some strange domains. It doesn't matter what the domain is. You don't fixate on domain. You would take the domain, the period of your parent graph, you divide it by the coefficient of the angle, get the new period, get the new intervals, and from that you would sketch to match what the given domain was. Okay, so that's as easy as a sketching of any graph that relates either to cos or to sine. They work in exactly the same way. I want my new period by dividing the parent period by the coefficient of the angle. I want then to establish what is the interval between my x-intercepts and my turning points, and I want to then adjust my sequence of y values to fit into that period. And once you've got that, you can go to the graph. And so what we would do is we now know that my graph will need 0 degrees, it will need 30, 60, 90, 120, and you keep doing that until you have reached the given domain, whatever that is. And so if that was 30 and 60 and 90, 120, we now have this new graph that starts at 1, 0, goes to negative 1, back to 0, back to 1, and you have my new cos graph. So you've adjusted the period, you've adjusted the intervals, and you can now keep on repeating that all the way through to infinity. Okay, so that's the cos function. Now, as I said, cos and sine work in exactly the same way. New period, new interval, and use the sequence of y values to sketch the picture. Tan works very differently. Actually, similar, but quite different. And why is that? Because a tan function has got a break in it. It's not like sine and cos, which oscillate between negative 1 and 1. The tan function looks very different. So let's have a look at that function. Okay, so change in period. The period change of the tan graph, and we're going to again look at the parent graph features of y equals tan x to sketch that graph. So what is peculiar to the y equals tan x graph? Okay, and I think what we'll do is, before we look at all that writing, let's just draw a graph of our tan function. So we have, different from sine and cos is that the tan graph has got a different period. The tan function has got a period of 180 degrees. Every 180 degrees, our tan cycle repeats itself. However, halfway between 180 degrees, you're always going to have a break in that curve. So if this is my 0 degrees and that is 180 degrees for my tan graph, halfway we're going to find an asymptote, which means that there is a break in the curve of tan. Another thing that happens halfway, so period, halfway asymptote, halfway. What happens at 45 degrees? What happens at 135 degrees? So look at how I'm discussing its properties and not just going to the calculator and point plotting. Is that if I've got an asymptote at 90, what is happening at 45 degrees? Every time you take the tan of 45, we get 1. And every time we take tan of negative 135, negative 1. This point guides us to indicate that because we've got an asymptote, this function increases but never crosses the asymptote, and this one here increases past negative 1, but it never reaches this line. And so we've got a break. But if we had to keep on sketching to the left, we'd actually find that this curve repeats itself on that side there. Okay, there's another break here, and it keeps on repeating itself, and it repeats itself there as well. Okay, but the purpose of my sketch is again to say, period is 180 degrees. What do I find halfway? Halfway, 90 degrees, I would find an asymptote, a break in the curve. And what do I find halfway? A very special point. It doesn't have a name, but it's 45 degrees 1. And we're going to use this very special point, and let's just call it the special point, in order to plot once we have a change in the period. Because can you see what's going to happen if I draw y equals tan 2x? Okay, something magical is going to happen. What about tan a half x? Something magical is going to happen again. I'm going to calculate the period. But whereas with sine and cos, we want to work the new intervals, these intervals are not based on maxima and minima because the tan graph does not have maxima and minima. So its range is actually negative infinity to infinity. Okay? So unique to the tan graph, does not have maxima, does not have minima. Therefore, it does not have an amplitude. Interesting. So in order to sketch the new tan function, we're not going to look at the intervals between maxima and minima. We're going to look at the intervals for the asymptote, and we're going to look at the interval for the special point 1. Okay, so let's go back over here. Use the parent graph feature. So whatever we found about the tan graph, we get period 180, we get halfway an asymptote, we get halfway a special point. So we're going to do the same thing for tan 2x. We're going to say, what's the new period? Well, what is the period of this graph, the parent graph? This period, it takes us 180 degrees. So the new period is going to be 180 degrees divided by the coefficient, which gives us 90 degrees. Okay, so from 0 to 90, I have to get a whole cycle in there. Halfway would be my asymptote. So asymptote in the period, in the 90 degrees, is going to be at x equals 45 degrees, halfway. And what are we going to find halfway between 0 and the asymptote? We're going to find the special point 1. So what I've called the critical value of 1 and negative 1 would be a half of our 45 degrees. So we would get 22 and a half. I'm going to sketch 1, and 45 plus 22 and a half, I would sketch my negative 1. So I've gone halfway between 0 and 45, and I've gone halfway between 45 and 90 degrees. So everything has almost concertinaed in so that we are getting things happening earlier. So if I take as a check mechanism, if I take 22 and a half and I multiply it by 2 and I take the tan of that, I'm going to get 1. You can do a double check, but don't waste time point plotting. Don't get yourselves comfortable in that point plotting. So my graph is now going to be, I'm going to have to get a whole cycle in here. So this is going to be my new asymptote. Then at 22 and a half, I'm going to get 1. At 67 and a half, here we go, I'm going to get negative 1. And so here's my tan function now. Okay, again, I could carry on there, and this is going to be my new asymptote, and I could carry on there and there. So as you can see, I'm getting 1 cycle and I'm getting 2 cycles in tan 2x, because that coefficient always tells me how many cycles I'm going to get in the parent period of the parent graph. Okay. Right. Let's see how we're doing. Okay. Okay, so the period is a very new concept for grade 11 mind-setters and everybody else out there that's grade 11 to be able to recognize that the change in the coefficient of x will affect the stretch, the horizontal stretch, as I call it, or the period. The larger the value after 1, the closer that graph gets, or it stretches or compresses, and the smaller that value, so a half x, for example, will actually stretch it out. Okay. Now, something you've done in grade 10 is actually your vertical shift. And your vertical shift, just basically, if you take your y values, they will be translated up or translated down, depending on the value of q. So here I had sine x as a parent graph, and then if I took sine x plus 1, can you see how every single y value has just gone up 1? So your period stays the same. Why does the period stay the same? Because there's no coefficient of x, or let me not say that. The coefficient of x is 1 for the angle. So sine x period is never affected if that coefficient doesn't change. But the graph has certainly been translated up or down. So let's just check here. Right, and the same thing with cos. If we look at the parent cos graph, and we go up 2, we go -1. So one graph has gone up 2 units, one graph has gone down 1 unit. So you translate up or down.
Okay, guys, thank you, Dina. Guys, thank you on our Facebook page. I see there are not so much questions as I expected. Turns out that you understand as far as I do, like I do, guys. But please, those questions on Facebook would be so much useful, guys. Remember, we're helping you to nail that exam before the end of the year, guys. But for now, let's take this quick egg break. Welcome back, Mindsetters, and yes, thank you guys for the love that you're showing on our Facebook page. One thing for sure, people like Fraser Temple think he's saying that it has become easy like ABC. Thank you, Mindset. No, we thank you for tuning in and being a Mindsetter. Now, that's what a Mindsetter does. Remember to visit our Facebook page. It's facebook.com/Learn Extra, and our website that you should always keep in mind or write it on your wall or something like that. It's learnextra.co.za/live. Now, time wasted never regains. Guys, let's go back to Dina.
Thank you, Tsepu, and thank you for those lovely comments, Facebookers or Mindsetters. I also know that some of you have made a comment about how fast it's going, yes. And I do apologize, but our show's only so long. You've got to speak to the sponsors and see if they can make it longer so we can spend more time with you. Right, the notes will be up, so you can go through the notes again and just go through it slowly and try and just let it sink in, because yes, I'm here just to present the notes, but you will need some time to just go back and try and sketch on your own what y equals sine 3x would look like. So use different coefficients. I've used 1, I've used 3 and 2, but try and use a half, try and use 4, and try and use it with the other functions, and just go and play with it. It really just needs a lot of practice, and then you'll feel a little bit better after you've done some practicing on your own. Right, so now we want to go back and do something else that's new in grade 11, and that is the horizontal shift, or as we've looked at in grade 10 at the vertical one, we're going to look at the horizontal one and what affects that horizontal shift. And for anybody who's already done quadratic functions, you'll be able to tell me that the quadratic's horizontal shift is guided by the coefficient, not by the coefficient, by the constant term inside the bracket that contains x. So taking that knowledge one step further, we would kind of expect a similar thing happening with our trig functions, is at the moment you add an angle to that x angle that you've already got in your parent graph, you are going to see something really nice happening. You're going to see some movements of that graph. And before we jump into it, I want to just first look at the parent graph features again of one of the functions, and then we'll look at how would we plot a graph that exhibits that kind of horizontal shift. Okay, let's have a look at the screen. I'm going to look at the graph of y equals cos x plus 30. And here I've got the features of the parent graph. So we've got the intervals between the maxima and the minimum, our quadrant angles, and they have given us trig ratios of 1, 0, -1, 0, 1. Obviously, between those, we're getting numbers between 1 and 0, between 0 and -1, etc. And what we're now going to do is to say, well, the graph of cos x plus 30 has to give us a 1. And where's that going to happen? Because we're not getting a period change, we're not getting an amplitude change, we're simply getting a new angle that's got to give us a value of 1. When is that going to happen? So mindsetters, you tell me, what do you think I should write over here as my x value in order for me to get a 1? Because that's really my starting point. My original 1 I got at 0 degrees for my parent graph, y equals cos x. I've now transformed it, and I'm saying, to get a 1, what must x be so that I would get a value of 1? Okay, and mathematics is all about inverses and going back and doing the opposite. Okay, so I think some of you are shouting at the screen and saying you definitely think that that should be minus 30. And the reason it's minus 30 is because the minus 30 plus the 30 would give us a 0. And that's when I'm getting a 1. I'm getting a 1 at 0 degrees. So the only time I would get a 0 degrees here is if x was minus 30. So I would need to zero that value, in other words. So if I start at minus 30, I would now get my maximum. Now, if nothing is affecting the x, if the x has got a coefficient of 1, its period won't change. So how many degrees does it take in the parent graph to get a 0 or to get a maximum or a minimum? It takes 90 degrees. So all you do now, if you've got that first angle that you've worked out for that maximum of 1, all you now need to do is add on 90 to get my 0. So 90 minus 30 would be 60. And you can now confirm it if you go back and say, well, what must x be so that you get a 0? X must be 60, because 60 plus 30 would give me the 90 degrees. So we're going back to giving me what was happening at 90. If I add 90 onto 60 degrees, I'm going to get 150. 150 plus 90 is 240, and 240 plus 90 is 330 degrees. And you'll see I did not use my point plotting on my calculator and punch in values. I am using my transformation of my y values and saying I still want a maximum to happen at 1. But how many degrees must I have in order to get a 1? I must have a 0 in here. I must have a 90 in there to get a 0. I must have a 180 in here to get a -1, etc. So I'm working backwards. But instead of looking at each one and taking 30 degrees away and 30 degrees away and 30 degrees away and 30 degrees away, we actually start with a 1 and then just add on 90. And as a check, you can then go back and insert it into your calculator to see if you've actually got the right thing. So it's very important as a mathematician to be able to verify, to have strategies to be able to verify what you're doing, to back yourself up that what you're doing actually makes sense. So we've actually got a transformation here that shows that this graph is exactly the same as that one, but everything has been translated 30 degrees to the left. Now, if you remember from your parabolas, you'll have noticed that if I sketch the graph of x plus 2, my turning point or my axis of symmetry is actually at -2. The translation is always in the opposite direction to what the function is given. So very important knowledge here while sketching that horizontal shift is always to get that first value, to understand what that first angle that you're going to sketch. Now you can go to your Cartesian plane and you can say, well, I needed 90 degrees splits. My intervals are 90 degrees, and I'm going to plot every 90 degrees, but I'm going to start at -30 and then work 90, until you've worked through the domain that the question's asking you to work with. Okay, so going back up, I've actually got that graph very nicely drawn for you. There it is. Okay, the x plus 30 graph. Let me just draw it in a bit more color, a bit more detail. It would be the one that starts at 1 minus 30, so it would be that one. And then it goes through 60, and it goes through there and up there, and it goes through here. So that would be my cos of x plus 30. This graph here, cos of x minus 45, what must x be so that I would get a maximum of 1? I need to zero that, so it would be at 45 degrees. So I've actually got my 45. Yeah, I think that's 45. That's the other way around. I should have drawn this one in yellow. That's my 45 there. Okay, and then this graph here, I wasn't looking clearly at the scale, but that graph there is the graph where we start at minus 30. So this value here is minus 30. Okay, and then minus 30 plus 60 gives me the 90, etc., etc. So that's actually the left translation, and the yellow one translates to the right, always in the opposite direction to what that value in that bracket is. So your domain was given, but your range, it's still minus 1 to 1. It hasn't been affected. Your amplitude is still 1, and your period, nothing has happened to the period. So everything is the same as the parent graph, except it just shifts left or it shifts right from that 0 degrees that we are used to. Okay, let's see this in action. In terms of what an examination question would look like. And I've taken the liberty to use Macmillan's grade 11 textbook, Clever, Keeping Math Simple, and just looking at two functions that have been drawn, sine 2x and cos of x plus 45. And they've given it to us in the domain negative 180 to 180. And just for better visibility, I'm going to sketch my sine 2x in blue. And I'm going to sketch, so that's F. And this graph here, I think it will look good if it is in yellow. So we're going to use a yellow. Okay. Erase it a little bit here and just fix it up there. Goes all the way up there. Okay, so they've actually labeled it for us. They've said that's definitely F, and G, that's the yellow graph there. The question is, write down the coordinates of the points A, B, C, and D. So A is this point over here, that's A. B is this point over here, C is that point there, and D is over here. Okay, now I'm not even going to look at the question. Okay, we've labeled it, we know we're looking at that. Let's engage with what has been given. Firstly, what kind of transformation is sine 2x from the parent graph sine x? What kind of transformation has that cos function undergone in terms of the parent graph? Okay, this one, what has been affected? The coefficient of x. This one, it's the term that's been added on. So what does the coefficient of x affect? The period. What does the coefficient, what does that constant term affect? The where you are starting with your maximum value of 1. So it will affect your starting value of 1. Okay, so engaging means let's go and work some things out. Okay, so let's work out. Let's go down a little bit and do some calculations, or actually let's go on to another page. There we go. So they've given us the graph, and we're going to establish in a moment whether we agree with them. Y equals sine 2x. Okay. Let's see. What is the period of this new graph? The period is my period for my parent graph, and I'm going to divide it by the coefficient, which is 2, so that's 180 degrees. Okay, what do we do after 180 degrees? Is 180 degrees good enough information for me to be able to determine where the maxima and minima are? No. I need to find the critical values at which these x-intercepts and maxima and minima are happening, so I need to find the intervals. And the intervals, there are 4 of them I need to plot. So it's 180 divided by 4, which is 45 degrees. Okay? So now I can say that my graph is going to have 180 degrees, halfway, I've got these. So these values are 45 degrees, and I'm going to get a 0, a 1, a 0, -1, 0, where 45, because that's my interval that I've worked out, plus another 45, plus another 45, plus another 45. So this is saying start at 45, add another 45, 45, 45. So every 45 degrees you're going to be oscillating between 1 and -1. Okay, so we can go back in a moment and just see, are we happy with this? And then the other graph that they gave us was the graph of cos of x plus 45. Okay, we know that the cos graph has the y value of 1, 0, 1. Okay, 1, 0, -1, 0, 1. And the question is, when is this going to be 1? When is cos of x plus 45 1? When x is minus 45. So we're going to start at minus 45. No period change. The coefficient is 1. So I'm going to keep adding in 90s. So plus 90 would be 45. Plus 90 would be 135. Plus 90 would be 225. Plus 90 would be 315. So we can go back and see whether we're happy that there is some intercept, some x-intercepts happening at 45 and at 225. So we now can go back to the graph, because the graph was empty. They gave us nothing. They just said, here are the curves. We can go back and fill those values in. So don't be guided by the questions, rather be guided by the interpretation that you can extract from what was given. Right, so let's go back there. Okay. So we said the period of my blue graph had been changed. So that has to be a maximum at 45 degrees. It cannot be anywhere, nothing else except this has to be 45 degrees, because this was a maximum of 1. Then it went back to a 0 at 90. Then it goes to a minimum at 135. And then it goes back to 180. And it's doing the same thing on the side. So it would have a minimum at -45. It then goes to -90, -135, and -180. So now what's left is for us to say what's happening with the yellow graph. We should have really made it yellow. There we go. Okay. The yellow graph, we said its maximum has to happen at -45 degrees. So there's its maximum at -45 degrees. There's its maximum of 1, so we're happy with that. 90 degrees later at 45, it's going to have a 0. We're happy with that. And then 90 degrees later, and at 225, it's going to have the next 0, but the graph stops at 180. So we could work out what is happening at 180 degrees. How do we do that? If we wanted to know what y value was over here, we would take 180 plus the 45, and we would get what the cos value is of that. Okay. So now that we've established what is happening with the scale, it gives us a sense that we understand what is actually happening here. So the coordinates of point A, we've actually now worked it out without even going to find them specifically, but that would be -135, that would be -90, and that would be 135. What is happening at C is that we want to know at naught what is my value. So I'll substitute in 0, and I would get the cos of 45. So this value over here at C would be a y value of √2 over 2. Okay. Interesting. What is the period of F? What is the period of the blue graph? So how many degrees does it take to get the function F? Well, how many degrees does it take? It starts repeating itself after that. So that's 180 degrees. Period is not a set. Period is one number, one value. Write down the period of G. What is the period of G? So how many degrees does it take to sketch the yellow graph? The period has not been affected. It's still 1x. So the period of the yellow graph is 360 degrees. The maximum value of sine 2x is 1, of course. And we'll end it off there. We hope that you had a good time with us.
Guys, I hope you enjoyed, but guys, time always flies. In this case, time is not on our side. Unfortunately, the show is over, but guys, remember to go to our website. It's landextra.co.za/live and go right there and get our notes. But for now, they are not there, but you can get them tomorrow. And we'd like to thank Macmillan for sponsoring the show. It was an awesome show, and we'd like to thank Dina for his awesome explanations. From now, guys, from me and Dina, we out, guys. See you next time.
And then I'm going to draw very selected trig functions which undergo the transformations of amplitude, period, vertical and horizontal shifts, focusing on these 4 transformations because that's what we'll be asked to sketch for examination purposes. What are the key concepts? And you've heard these words before, so just to revise them, domain is the set of all the x values which a function can have. And in terms of trigonometry, we're looking at how many degrees a function can take on. The range is a set of all y values which a function can have. So domain is the x. And if you remember that domain starts with a D, and that stands for our x values. Range starts with an R, and that's for our y values. So x, y, domain range, so that you don't get those 2 words mixed up. The amplitude of a graph is always defined as the difference between the maximum and minimum y values. And the period of the graph, very specific definition for period, it's the number of degrees that the curve takes to complete one wavelength. So we'll look quite intensely at the period of functions. Having said that with our key concepts, I want to now look at the graph of y equals a sine x, which we are calling as a change in amplitude.
Just have fun, guys. Trigonometry with Dina. Dina, you can take the board. Okay, but before she does that, guys, please, on our Facebook page, ask as many questions as you can. Challenge me as hard as you can, and I'll ask her as many questions as I can. But for now, Dina, take it over.
Thanks, Tepu, and welcome grade 11s and maybe some grade 12s. We're doing some revision and some grade 10s if you just want to extend your knowledge. So let's have a look at some of the trig functions. You did in grade 10 look at the transformations, changing the amplitude and changing the vertical shift, but today we're going to look at some period changes and we're going to have a look at some horizontal changes. So those are the 2 new changes coming in. So we will revise very briefly what the amplitude change does, and we will look at some key concepts as well, but let's go straight ahead and see what the objectives of our lesson are for today. Okay, in this lesson, we're going to revise the terms that we use, often used in trig functions and in some other functions as well. We're going to look at domain, range, amplitude, period, maxima, and minima values. We're going to investigate the parameters A, B, P, and Q on the parent trig graphs, so that we'll eventually look at what does A sine bx plus Q as well as y equals sine of x minus P looks like. And then we're going to do that for the other trig functions, the cos function and tan function as well.
Welcome, mindsetters. How are you? I am Tepu, guys. Guys, a little bit tells me that you grade 11s have been waiting anxiously for your mathematics. And guys, helping us today is our awesome teacher, Dina. How are you, ma'am?
Hello, Tepu, and hello, everybody else.
What are we doing today?
We are doing some trigonometry, some trig graphs. The grade 10s have just left off some trig graphs, and we're just continuing with the graphs as well.
Grade 10s, if you're watching, you can still join us. You're welcome just to step up your game a little bit and surprise your teacher. But for now, Dina, you can take the board.
Thanks, Tepu.
Guys, while you're on that one, remember to visit our website. It's landextra.co.za/live, or simply go to our Facebook page and like it. It's facebook.com/ Learn Extra or follow us on Twitter. Simple as that. It's at Learn Extra. Yeah. And guys, we thank Macmillan for sponsoring the show. All the notes that we'll be using today are from the Macmillan textbook. You can go and get it, the grade 11 version. Or simply, guys, don't forget to go to our site and go to our site, I meant to say, and simply download the notes for today's show and do with them at home and paste them on their walls, on your whatever.
And the graphs have been sketched for us, and just below the graphs, we've got a table that just shows us those key features: the domain, the range, the amplitude, and the period. And if I had to draw the parent graph, the sine parent graph, then it would look something like this. We would have a maximum at 90, we would have a minimum at negative 270, and a 0. So continuing the cycle this way, we would have these values, so that our sine graph, or what we call our parent graph, would have a range that goes between -1 as the minimum to 1. So all my sine values are found between 1 and -1. And we're now looking at the graph y equals 2 sine x, which is this graph over here. And we're looking at the graph of y equals -1 sine x, which is this graph over there. So just to talk about it, you'll see that the yellow graph has got a maximum at 2, and the purple graph has got a minimum at -1. So looking at the range, it's still -1 to 1. The range is still the same. The range for the yellow graph has changed because the coefficient is now 2. So changing the coefficient of the trig function will change its maximum and minimum values. And the way that we can actually plot those is very easy, because our parent graph has got y values that start at 0. So this is just my y values. They would be 0, I go to 1, I go back to 0, I go to -1, and I go back to 0. So my quadrant angles, 90, 180, 270, 360, have got these critical maximum, minimum, and 0 values. And if I want to then see what is the effect of that coefficient of the ratio, I would multiply each of those y values by the new function, or the new coefficient a, and I would now be able to get what those new critical values would be. So the amplitude, very easy to work with. Take your parent graph, multiply it by the new coefficient, and we've got the yellow graph if it's 2, and we've got the purple graph if it's 1, if it's -1. -1, notice, it's just the reflection of the blue graph about the x-axis. So we've inverted every single blue value by a value of -1 across the x-axis. So that would be our amplitude change.